we continue our discussion of the electric field for the case of conductors. Now we are going to talk about the cavities. So a cavity is some kind of a insulating region, a non-conducting region placed inside a conductor. So it's completely surrounded by a conductor, right? So everything around the cavities is actually a conductor. What's so significant about them? So I'm going to draw this picture again. So this is basically for describing what a cavity is. So let me draw this picture again, but this time I'm not going to use. I'm not going to do a shading of that region. So let's say that this is the cavity in here, and this is the conductor, right? So as a result, there is this inner surface of the conductor in here. So that's the part of the surface. And the conductor also has this outer surface in here, in the outside. So we know that, again, in the static situation, all of the charges on the conductor should be collected at the surfaces. So either the inner surface or the outer surface, or both of them, should have some kind of a charge distribution. So in which case the inner surface should have a charge distribution. This only happens if there's some kind of an inside the cavity, there's some kind of a charge. So let's say that I have just a single point charge inside. It doesn't matter where, and it doesn't matter how it is placed. So suppose that there's such kind of a charge in here. So as a result, there has to be an electric field inside the cavity. So blue lines are basically the electric field lines. And there can be an electric field outside too, but in any case, I know that the electric field is zero inside the conductor. So as a result, based on this, can I say that there has to be some kind of a charge distribution on the inner surface of the cavity? So that's the question in here. And the answer is yes. So the only thing that we need to do is to draw a Gaussian surface in here. Choose the Gaussian surface in such a way that all parts of the surface is inside the conductor, which means that at all points on the surface of the Gaussian surface, the electric field is zero. So that means the flux is zero in here. However, the Gaussian surface encloses the whole cavity. And so as a result, if you just use the Gauss law for this situation, so that's that integral. So that's equal to the enclosed charge. So since the electric field is equal to zero at all points on the surface, the flux integral is equal to zero. What's the enclosed charge? The enclosed charge is the charge, basically inside the cavity. Inside cavity, let me write it down like that, plus the charge collected on the cavity surface. So that's basically the charge on the conductor. So in this situation, for example, the charge inside the cavity is Q. That's the point charge, and so therefore there has to be some kind of a surface charge on the cavity so that their sum becomes equal to zero. So because the left hand side is equal to zero, so there has to be some kind of a charge collected in here, and that charge should be negative. So therefore, a minus Q basically, right? So there should be some kind of charge collected at the surface of the cavity so that we have some zero thing in here. So just keep in mind that this is for ensuring that the electric field is zero inside the conductor. So let me describe the situation, how such kind of a surface charge distribution is collected at the cavity surface. Sorry, let me draw a bigger cavity in here. So again, let's remember that this is the conductor, and this is the cavity. But I'm going to erase this cavity thing. So suppose that I place a positive charge in here, and this is beginning right before the static situation is established. Right? In that case, I know that this positive charge produces an electric field like that. electric field like this, electric field lines like that, right? I'm just going to draw only a few, which means there will be an electric field inside the conductor now, and so therefore the negative charge carriers in here will be accelerated towards the positive charge. But of course they cannot be accelerated forever because they have to get stuck at the surface somehow, right? So as a result, there will be some kind of a collection of negative charges at the surface in here. Let me do an undo, and then I'm going to draw an alternative situation in here. So eventually, when we start collecting these negative charges at the surface, so there will be some kind of a negative charges collected. Perhaps the current has not stopped at that point. So in that case, we are going to have situations where, well, these electric field lines are not straight lines anymore, because they also contribute something to the electric field. But I mean, there might still be some kind of electric field left inside the conductor. As long as an electric field is left, this charge flow is going to continue. And so as a result, these negative charges will flow towards the cavity surface, right? So therefore, we cannot establish the static situation until the electric field becomes completely equal to zero. So as a result, eventually, let me do an undo again. Eventually, we are going to reach a situation where the electric field inside the conductor becomes exactly equal to zero. How is this possible? So I know that at every point, this positive charge produces, every point inside the conductor, this positive charge produces an electric field like that. So let me call this as E plus. But there are also negative charges in here. So all of these negative charges also produce some kind of electric field at that point. And since we have too many electric charges at different places, we have lots of small electric field values in here. In any case, the electric field produced by the negative charges are opposite direction almost, but their sum should be equal and opposite to this thing. So as a result, their sum somehow becomes equal to zero. Right? So that's the conclusion, therefore. If I place a positive charge inside, so let me draw it like that. If I choose place a positive charge inside a cavity, so somehow there should be some kind of negative charges collected at the surface in such a way that the total contribution of all of the negative charges and the positive charge inside the conductor is equal to zero. So as a result, this negative charge distribution should be a very special charge distribution, actually. So there's an electric field inside the cavity. Well, that's an insulating region, so therefore there is no problem if there's an electric field in here. These electric field lines start from positive charges and end up at the negative charges, right? That's okay. If I move this positive charge somewhere else in the cavity, in that case, this pattern and the negative charge distribution in here is going to change. So for example, let me raise all of this. Suppose that I still have the same amount of charge within the cavity, so that's plus Q, but I placed it in here. So probably in that case, I will have more negative charges in this region and less negative charges in these parts of the cavity, because only with this kind of a surface distribution we would have the electric field zero in this case, right? In this case too, there will be some kind of electric field lines in here, but most of these lines will be somewhere in this region. In any case, so therefore, that's basically the conclusion. If I have, right, I'm going to draw it again, same kind of a picture, repeating the same argument. If I have a charge Q placed inside a cavity, so this cavity surface should somehow collect a total charge of minus Q in such a way that their total effect in terms of electric field inside the conductor is zero. So these negative charges somehow cancel the effect of this point charge in this region inside the conductor. these negative charges do not cancel the effect of Q inside the cavity. So inside the cavity there is some kind of a net electric field, but apart from that, outside, well, it's outside the cavity, but inside the conductor, their net effect should somehow cancel each other. Another thing, if I don't have a single point charge, but 2 point charges inside the cavity, let's call it at Q1 and Q2. In that case, at the cavity surface, amount of charge that should be collected is equal to minus the total amount of charge within the cavity, right? That's the rule basically. Okay, then we have this situation. So that's quite hard to understand at first sight. I'm just going to draw a circle in here and let me make it a little bit perfect circle. All right, so let me do it like this. So this is a metallic conductor. Let's suppose that this is a conductor. This is a metal. But it has a cavity, and the cavity is like irregular in shape. So the sphere has the perfect spherical symmetry, but the cavity does not have this spherical symmetry. And somehow I have the charge Q inside, or let's say 2 charges. I don't know. It doesn't matter what it is. So I know that at the end, and let's suppose that the conductor's net charge is equal to 0. So net charge on conductor is given as 0, and charge inside cavity is charge inside cavity is equal to Q. In that case, we know that some charge will be collected at the inner surface of the cavity. How much charge? Well, we know the answer. It is minus Q. So that minus Q and Q in here, they are going to add up to equal to 0. And well, this is necessary for the cancellation effect, because I know that if I use a Gaussian surface like that, the flux should be 0. So therefore, the total charge inside the Gaussian surface should be equal to 0. So that's something that I know. All right, so if there's a minus Q charge collected at the inner surface of the conductor, so that means that there is a plus Q charge. Let me use a white color for that. A plus Q charge would be collected at the outer surface. Okay, so plus Q will be collected at the outer surface. All right, so we have said that somehow the point charge inside the cavity and all of the charges inside the cavity surface, they cancel their effect. So as a result, I'm just considering these 2 charges only, right? The point charge inside the cavity and all of the charges at the cavity surface. I know that their combined effect is some kind of an electric field inside. There's some kind of an electric field inside, whatever it is. But their net effect on the outside is equal to 0. And outside but inside the conductor. But somehow, because of the electromagnetic laws, if they cancel their effect in the spherical region, they also cancel their effect at every point outside. So as a result, the combined effect of both of these charges inside the conductor or outside the conductor, that's equal to 0. So somehow, if you have a point in here or inside the conductor, I can safely neglect the point charge inside the cavity and the charges inside the cavity surface. So I can treat this problem as if this part of the problem doesn't exist. Okay, so that's important actually. And so as a result, from this point of view, this whole distribution is equivalent to a distribution of a charge at the surface of the conductor. Okay, so that's there's a plus Q charge distribution at the surface of the conductor. In reality, there's some kind of a cavity in here, and there are some distributions in there, but they don't have any effect outside or inside the conductor. And so as a result, I just forget about them. Now the question is, How is that plus Q distribution, plus Q charge at the outer surface is distributed? I know that because of the spherical symmetry, this has to be distributed uniformly. Because I know that this distribution should be in such a way that the electric field produced by that positive charge distribution at a point inside should be zero. So all of these positive charges should be distributed in such a way that the electric field inside is equal to zero. And I know that I have solved this problem before. If I have a uniformly distributed spherical shell, thin spherical shell, that distribution doesn't create an electric field inside. So therefore, for that situation, that charge should be uniformly distributed. Okay, so the significant thing in here is that even though the problem does not have the spherical symmetry because the cavity surface is irregular, because of the fact that we somehow took the cavity out of the question, now the problem reduced to a problem with spherical symmetry. In which case, there's some kind of a charge distributed over the surface. It has to be distributed with the same symmetry as the sphere, so it has to be distributed spherically symmetric way. In which case, the electric field inside is equal to zero, so that's consistent with our expectations because there's a conductor inside. And so therefore, at any point outside, the electric field can be said to be equal to this expression given by the Coulomb's law. All right. So therefore, coming back to the same question, let's erase this now. All right. So at this point, for example, at an outside point, let me choose a point somewhere else. Let me erase this. Let me choose a point somewhere in here. Let's say that this point has a distance r to the center. And I would like to find the electric field at that point. So let me use a blue color for the electric field again. So I'm claiming that the combined effect of the charge inside the cavity, charge on the cavity, inner cavity surface, and charge on the outer surface of the conductor is 1 over 4 pi epsilon 0 q divided by r squared. Why? Because these two, they cancel their effects, so therefore I just forget about them. This electric field is produced by the outer surface distribution of the charge in here. I can think of it like that. And in that case, I can use the Gauss law to compute that quantity. Okay.